So yeah, in this case, you have to modify your element stiffness matrix and your force vector. Right, so you can express the bubble displacement in this form, and if you take this bubble displacement and plug it back into the remaining equations, which is right here, this gives you the form for the stiffness matrix and the similar form for the element force vector. So you have to modify the element stiffness matrix like this and modify the element force vector like this. Were you guys able to get the same answer for the 7 cross 7 and 4 cross 4? Yeah? Okay. Had a question? You had a question or what? Oh, you got it. Great. Good job. Okay. How about the abacus and the truss thing? To what precision are you guys getting the same answer? Like 7th digit, 10th digit or something? Really close? Yeah. So, well, that's good. All right. Any other questions? Okay. So let's see. We were doing last time the finite element approximation for 2 dimensions and 3-dimensional problems. So we started to take a look at the thermal heat conduction problem, and we said that the sample problem that we were going to look at was this one, this domain. We used the method of weighted residuals. We take the governing differential equation, multiply it with a virtual temperature field, integrate it over the domain, and do our integration by parts in 2 dimensions or 3 dimensions. And we also need to make use of the divergence theorem, which just allows you to convert any integral that has a derivative over the domain to the same integral over to the integral over the quantity of the same quantity over the boundary of that integral. So we saw that we came up with very similar form that we had in 1 dimensions. So we called this internal virtual work, external virtual work. So this is not really virtual work, this is a thermal heat conduction problem, but these are terms that are similar to those. And then we said that we were going to discretize our domain. So we have set up our weak form over the entire domain. Now we want to sum it up over small elements in the domain. So we talked about a couple of discretization techniques, and then we started to take a look at the finite element discretization using triangles. How would that look? Okay. So we said that we are going to use the very similar formula to what we were doing in 1 dimension. We said in 1 dimension that our displacement was going to be n some matrix times the degrees of freedom at the nodes of the element. So if this is a 1-dimensional element, it has only 1 degree of freedom per node. In that case, this d vector would be 2 cross 1, and this n vector would be 1 cross 2. But in this case, since this is a 2-dimensional problem, and for now we are considering a triangular element which has 3 nodes per element, therefore we will have 1 shape function for each node. And if we can approximate our solution, this is the temperature field within the element. So you go to any point x, y within the element, you can calculate the approximate value of temperature at that point, any point within the element, using this expression. And we also saw that what this really physically means is that we have expressed the temperature field over the element in terms of its nodal values. So let's say the nodal values are these DE1, DE2, DE3. If you just draw up, so these are 3 points in space, you can just pass a plane through all those 3 points, and all the values within the plane you can calculate with this expression, n times d. So that's just a linear interpolation of the values of temperature between the 3 points of between the 3 nodes of the triangle. Then we also saw that if we use this discretization or if we use this approximation, we can also express our temperature gradient with a similar form. This is the B matrix, which is the matrix of derivatives of shape functions. So if you use the derivatives of shape functions multiplied with the same degrees of freedom that we had here. So this is temperature multiplying with is equal to shape function matrix times degrees of freedom at the nodes. The same degrees of freedom at the nodes, if we multiply B by those degrees of freedom, what we get is this temperature gradient vector, okay? And we talked a little bit about how these hat shape functions or tent shape functions are very very similar to what we had in the one-dimensional case. So they are zero pretty much everywhere outside the immediate domain of the of that node. And if you try to calculate the derivatives of this shape function within each triangle, it would be constant. Okay, so and we said that since these derivatives are constant but they are discontinuous, even then the square of those derivatives is going to be integrable. So our method of weighted residuals is valid if we choose these kinds of approximations. Okay, and then so yeah, we started to derive how we can calculate the actual value of or actual function, actual expression of all these n1, n2, n3 shape functions. So this is what we were doing last time. We said that we can express our approximation using a Ritz method. So we know that this is a linear approximation. There is a constant term and an x term and a y term. So using Ritz approximation, we can express it like this. And since we know that it has to pass through those 3 points at the nodes, we have these 3 equations. So if you plug in the coordinates of the first node, x1, y1, you should get the value dE1, which is right here. If you plug in the value x2, y2, you get d2, which is right here. Plug in x3, y3, you get d3. So you get these 3 equations that will allow you to express the shape function, the approximate value of the temperature within the element in terms of its n shape functions instead of the h shape functions. But last time I think I made a little error here. So please make a note of that. In this term, I had used small letters for A1, B1, C1, and so on. So those are not small letters. We need to distinguish them from these A1, A2, A3. So these are big uppercase A, A1, B1, C1, A2, B2, C2, and so on. Okay. So what we can see is that all that you needed to do to calculate the expression for n1, n2, n3 in this case was to just solve this 3 equations, 3 unknowns for A1, A2, and A3. If you do that and plug them back into your original or into this equation right here, if you plug them back in, you will get this form. And then if you collect the terms, d1, d2, d3, then you will see that this is n1, this is n2, this is n3. And we'll do an example about this in a minute, but there's some interesting properties of these shape functions. So what do you think, what will I get if I sum up the values of these shape functions at some general point x, y? So let's try to do that. So if I say sum of shape functions, let's say alpha at x, y, where alpha goes from 1 to 3. So all I'm trying to do here is sum up all the shape functions at a general point within the element. So this is nothing but n1 x comma y plus n2 x comma y plus n3 x comma y. And what we would get in this case is A1 plus A2 plus A3. This is the constant term, plus we would get B1 plus B2 plus B3. This is the X term, and plus um, C1 plus C2 plus C3. This is the Y term. Does that sound correct? So what is the value of this term? B1, B2, B1 plus B2 plus B3. If you sum up the middle row right here, what do we get? 0. So this term is 0. How about this term? This is also 0. How about this term? This is not 0. But if you try to calculate this, this is going to be the sum of this plus this plus this. So can anybody take a guess what this is? It is the determinant of the matrix that we defined. Let's see somewhere. Yeah, right here. It is this determinant. So this is just equal to 2 delta. Okay. So what we get is 2 delta, and actually we have a 2 delta sitting outside right here. 1 upon 2 delta. So if we add that in here, we get 1. And this is a very important property of almost all finite elements. The sum of shape functions at any point within the element turns out to be 1. And this is an important property that is called completeness. And we'll take a look at that a little bit later in a few lectures. What are the requirements for the convergence of finite elements? Meaning that if you keep on dividing your domain into smaller and smaller triangles, will you converge to an exact solution, or will your solution start to diverge? So this property, that sum of the shape functions at some general point within any element has to be equal to 1, is called the completeness requirement. Okay. All right. So let's. We said that we are going to take this expression for approximation that we have here, n times d, theta is equal to n times d, and we are going to substitute that into our weak form. And if you do that, we went through most of the steps of this algebra, but what we get is, in the discretized version, what you would do is, since this theta is equal to the matrix times the degrees of freedom at the nodes, your temperature gradients can be expressed with the derivatives of the shape function matrix times the same degrees of freedom. And if you plug them in, what you get is the familiar form that we had before: sum over all the elements, d transpose some element stiffness matrix times the element degrees of freedom times the virtual displacement. I think there's a bar missing here. So this is the virtual temperature field times the element force or heat flux vector in this case. And if you try to rearrange these equations into, or by assembling them for all the triangles in your domain, then you can write this out like this. All you're doing is d. This is the virtual temperature degrees of freedom within each element times kd, and this is the heat flux within each element. And if you assemble them, this A denotes the assembly operator. You get this familiar equation that we used to have even before in the one-dimensional case. Okay, so this is the standard procedure for all types of finite element formulations. You try to express, you discretize your domain, make sure you use an approximation n times d, plug that into your weak form, and you will be able to come up with this kind of a form that you can then implement on a computer. So here's a little bit of a note about how to do assembly operations in 2 dimensions and 3 dimensions. So if you remember from 1 dimensions, what we had was, if you have a long bar, you chop it up into small parts. We said that the degree of freedom from one element on the left side is equal to the degree of freedom on the right side of from the next element. So in this case, we since this is a scalar problem, we still have only 1 degree of freedom per node. So what is that degree of freedom? The temperature at that node. So this is the same square domain with top uh, the top edge that is at a higher temperature, lower edge at the lower temperature, and so on. All we are trying to find out is the temperature profile within this domain. So if we can express, or if we can solve for the temperature values at all these different nodes, then using our shape functions, we can go back and calculate what is the temperature at any point anywhere in the domain. Okay. So in this case, when we want to assemble these equations, I'm denoting the total number of nodes in your domain with big N, total number of elements with big M. And since this is a scalar field problem, you have 1 degree of freedom per node, which means that your degrees of freedom is equal to the total number of nodes in the problem. And then, just like in the one-dimensional problem, you had this big global stiffness matrix, and you were substituting you were adding 2 cross 2 small element stiffness matrices to that big global matrix. The same sort of idea is going to hold here also. So, for example, if you consider some element E, which has global node numbers I, J, K, it has local degrees of freedom 1, 2, 3, then you will see that the local stiffness matrix is going to turn out to be a 3 cross 3. Is that right? So because since there are 3 nodes, you will have 3 cross 3 local stiffness matrix. And you need to assemble this local stiffness matrix into a global stiffness matrix. But unlike the one-dimensional case, what happens here is that this local degree of freedom 1 corresponds to the global degree of freedom I. And here, same way, global degree of freedom I. The local degree of freedom 2, that corresponds to J, this row and this column. The local degree of freedom 3 corresponds to K, which is this row and this column. So you might have to rearrange your element stiffness matrix to add that contribution to the global stiffness matrix. But the idea is the exact same that we had in one dimension. All you're doing is you're trying to make sure that, let's say, this 1 cross 1 component, this one, needs to go to I cross I. Right? 1 cross 2 component needs to go to I cross J. 1 cross 3 needs to go to I cross K right here, so on, right? So in MATLAB, I also told you, and actually you can see that from the solution for the homework problem 3 that I posted. I created a vector called LDOFs, right? So that vector just records what is the global degree of freedom of that element. So in this case, the global degrees of freedom of that element is I, J, K. So for example, let's take this element 5. The global degrees of freedom of this element 5 are 4, 6, and 7. So these I, J, and K are 4, 6, and 7. And all you need to do is, after you calculate your 3 cross 3 element stiffness matrix, you need to just go to the corresponding degrees of freedom here. In this case, they won't be numbered as I, J, K. It would actually just be 4, 6, and 7. Does that? So assembly procedure is very similar to what you had in one dimension, but all you need to do is the exact same formula that you had in that MATLAB code about K global LDOFs, LDOFs is equal to K global LDOFs, LDOFs plus the element stiffness matrix. That will automatically take care of your assembly routine. Okay? So in MATLAB, assembly is really straightforward. You don't have to think too much about that. All right. Any questions on this assembly? Any doubts? No? Okay. All right, so let's take a little bit of an example here. Let's say we have this element we are calling omega e, and this element has the coordinates 2, 1, 5, 3, and 3, 4. So these are the coordinates of some element which is a part of a big mesh. Okay, and what we want to do is to first find out what are the shape functions for each of the three nodes n1, n2, n3. We want to find out what are the derivatives of those shape function matrices, and we want to find out the stiffness matrix. And by the way, there is a handout for today. If you don't have it, anybody need a handout? Okay, so please circulate that. Um, so, all right. So using uh, using these coordinates, we need to come up with the shape functions first, right? We need to find what is the expression for n1, what is n2, and n3. So we are going to use the same procedure that I just told you about. This was how to obtain the shape functions for n. So we are going to say that the temperature at a point, at any general point within this triangle, is going to be approximated with our Ritz approximation. We know that the temperature profile within the triangle, we want it to be linear. Therefore, our Ritz approximation is just the a vector dotted with the h vector, which turns out to be a1 plus a2x plus a3y. So this is a linear approximation. All we need to do now is to plug in the coordinates of our nodes. So we know that the value of the temperature at node 1, we want it to be dE1, which is still an unknown. We are going to solve for this, but we are doing this to find out what is the function form of this n matrix. So we want that nodal temperature to be dE1. That has to be equal to the coordinate of this point 2 and the y coordinate of this point here. That gives us one equation. Similarly, you plug in the coordinates of 2, 5, 3, that's right here, and 3, 4, that's right here. So this gives you three equations, and the three unknowns in this case are a1, a2, a3. These are the coefficients of your Ritz approximation. Okay, and the right hand side, you can we are going to, these are the unknowns that we will solve for later, but right now we are going to treat them as knowns because we want to express these shape functions in terms of x and y. So all that we need to do now is, this equation you can see is nothing but this is the right hand side vector, this is the left hand side matrix, if you will, and the unknowns are a1, a2, a3. So if you take that matrix, that's 1, 1, 1, and 2, 5, 3 comes from here, 1, 3, 4 comes from here. So if you were to write that in the matrix form, Ax is equal to B, this would be your matrix A, this would be the unknowns x, this would be the right hand side. And all I'm doing is trying to calculate A1, A2, A3. And if you invert this matrix, you get this matrix. So the inverse of this matrix becomes this. All you need to do now is to expand this out, and what we get by expanding this out, what we'll do is we'll substitute the values of A1, A2, A3 into our original approximation. So if we do that, you can see that this is the first row, 11 minus 5, 1 times D1, D2, D3, right? That's right here. And then you have minus 1, 3, 2, that's minus 1, 3, 2, minus 2, and then minus 2, minus 1, 3, which is right here. And if you collect terms now for D1, this D1, this D1, and this D1, that goes right here, and what you're left with is your shape function matrix. So the idea here is that if I give you a set of nodes, nodal coordinates x, y, okay, like the next homework problem will be this. You'll have x, y coordinates of some points. I'll give you the connectivities of each of those triangles, and I will, what you will need to do is to generate this n functions just using exactly the same procedure, and you are going to then try to generate the derivatives and generate the element stiffness matrix, assemble them and solve it. Okay, so that's the same procedure that I'm describing to you now. Um, Now that you have this n1, n2, n3, the shape function matrix is simply a 3 cross 1, or sorry, 1 cross 3, 1 row, 3 columns. The derivatives of those shape functions, these derivatives were coming from the temperature gradient. So if you go back and maybe take a look here, um, sorry, yeah, here. So this is the temperature gradient. We said that the temperature gradient vector is simply the gradient of derivative of the temperature with respect to x1, derivative of temperature with respect to x2. And if you use the approximation n times d, then the derivatives of the temperature gradient can be written in terms of b times d, and this becomes your B matrix. So in order to calculate your B matrix, all you need to do is take your n matrix, take the first row derivative with respect to x1, and take the second row derivative with respect to x2, and that's what we are doing here. So you take this n1 derivative with respect to x. What is that going to be? Partial derivative with respect to x, that's minus 1 right here. N2 partial derivative with respect to x, 3. N3 partial derivative with respect to x, minus 2. And similarly for partial derivatives with respect to y, we will have minus 2, minus 1, 3, minus 2, minus 1, 3. So it's really not very complicated to calculate all these things. You just have to get the hang of the procedure, and then you will be able to code it up easily in MATLAB. So once you have this B matrix, all that you need to do then is to substitute it into the expression for your element stiffness matrix. So let's see what this comes out to be. In this case, I'm saying that the this kappa, this is the conductivity tensor. We are going to assume that the conductivity tensor is some scalar times identity. Okay, so if I use that assumption, then I can pull this kappa out of the integral. It's just a scalar, and you have B transpose B. So if you take the transpose of this, that's this matrix right here, and this is the B. And what do you think? How do I integrate this? Any ideas on how do I find the integral of this matrix? What would be the result? What would be the size of the resulting matrix? 3 cross 3. And the elements of that. So let's do that. This would be equal to kappa integral omega over the domain. The first element is going to be 5. Second element is going to be minus 3 times plus 3, is it? No, minus 3 times plus 2, minus 1. Minus 1, minus 2, so this would be 2 times minus 4. And 3 times minus 1 would be 9 and 10. And you would have minus 6 and minus 3, minus 9. And you would have minus, so this would be 4 plus 9, 13. And the rest is symmetric. So it's just make sure that this algebra is correct. So this is a constant matrix. It does not depend upon x or y, right? So can I pull this out of the integral? All right, so let's pull this thing out of the integral. And what we are left with is this. So what is this quantity now? Sorry? Yep. Sorry? Yeah, it would be a double integral if it is a square domain, but we are talking about this triangle. So all we are doing is we are integrating 1 over that domain. So what should we get? If okay, so let's take a one-dimensional case. If you take a one-dimensional case, if you integrate 1, you just say integral dx from xe to xe plus 1. What is that? L, length of the element. So what would this be? Area of the triangle, right? So we have area of the triangle. Um, so all that this becomes then is kappa times A times the same matrix. And now all that you need to do is to take this. This is the element stiffness matrix. You can similarly calculate your element force vector and plug it into your global stiffness matrix. Just assemble it into your global stiffness matrix. And that's the way pretty much you would be solving a heat conduction problem. Any questions on this? What's that? Kappa is conductivity. So we are assuming that this is that kappa tensor. It's generally a 2 cross 2 tensor. But in this case, we are assuming that this is an isotropic material. So we can express it as a scalar times identity. So this is, at the end of the day, you need to be able to understand the procedure, and then the rest of it is just math, just algebra. So the idea here is you want to solve some differential equation over a complicated domain. And you first take your differential equation, express it into a weak form, and discretize that weak form using finite elements. Within that finite element, you use an approximation in terms of the shape functions. Using that approximation, you come up with your matrix equations. That's it. That's the standard procedure for all types of finite element formulations. The details are a little bit different for each type of problem, and the real trick is really about when does this thing work, when does this thing fail. So one condition I just told you today is the sum of the shape functions need to be 1 if you want to have complete shape function basis. So that is one of the requirements for finite elements in order for them to converge. But there's a couple more requirements. There may be many more actually, but we'll go over them when we get there. So all right, so this was the heat conduction problem where what we were trying to solve was the value of the temperature at each of the nodes. This was a scalar problem. So now we are going to take a look at the elasticity problem in 2 dimensions. So this is also something that we had started a little earlier, but let's go over this for a little different problem. Here is a cantilever beam, and actually let me not call it a beam. This is a 2-dimensional domain. It looks like a beam, but beam is a 1-dimensional problem. So this is a cantilever domain, let's say. It is fixed at the middle point right here, and the rest of the edge is on a roller support. There is applied uniformly distributed or some sort of a distribution load here on the top edge, and the rest of the edge is free. So the domain is going to be our this rectangular domain, and the free portion of the boundary, gamma n, is going to be this top edge, this free edge, and this bottom edge. So the reason that we are including these also because the traction is specified on that edge. What is that traction? 0. So the traction is specified at all of these edges. On this edge, it is the traction is specified to be Tn. On these edges, it is specified to be 0. On the other hand, the displacement is specified to be 0 at this point in the x and the y direction, and the displacement is specified to be 0 in the x direction along this edge. So those are our boundary conditions, and we know that the governing differential equation for elasticity is the same old div of sigma plus b is equal to 0. We take our governing differential equation, we multiply that with a virtual displacement. Now note that this virtual displacement is also a vector. So I'm I'm denoting that vector with u bar for the virtual displacement. The top bar is for the virtual displacement. The bottom bar is to show that it is a vector. Okay. Divergence of sigma, the result of this is going to be a vector. Sigma is a tensor. Divergence of a tensor is going to give you back a vector. So one vector plus another vector, you can dot that with this vector. And what you would get is a scalar. So all we are doing is that the result finally G has to be a scalar. So this is the this is the method of weighted residuals from which we will derive our weak form. So to derive the weak form, what we are going to do is to express this using the initial notation. So divergence of sigma is nothing but sigma ij comma j, where comma j just denotes derivative with respect to xj. And once again, we are going to use the summation convention, that since j is repeated, it needs to be summed up 1, 2, and 3 in 3 dimensions. Okay. Similarly, I is also repeated. I is repeated here and here. So when you multiply this term out, you will have to have 9 terms in 3 dimensions, or you would have to have 4 terms in 2 dimensions. And another way to see that this is a repeated index is that if you take u bar I, which is a scalar quantity, and dot it with the body force ui bi means u1 b1, u2 b2, u3 b3, right? So that is also a 3-term summation right here. So now we are going to try to balance the derivatives. We know that there is no derivative on the virtual displacement right now, just like we had in one-dimensional case. But on the other hand, the stress sigma itself has a derivative of u of the real displacement sitting in there, and on top of that we are taking another derivative. So there are 2 derivatives for the displacement in this term. So then what we'll do is just use our product rule, or integration by parts. And integration by parts for the elasticity problem is a little bit different than the heat conduction problem, but let's take a look at this. So let's say we are going to consider this quantity ui bar times sigma ij, and there should not be a comma j inside. So make that correction. So if we consider this quantity, we take the derivative of that with respect to xj. What we are going to get using the product rule is take this derivative of this quantity first times sigma ij plus the same ui bar times divergence of stress. So this right hand term is the exact term that we have here. And so we can also express this right hand side term using the just rearranging terms. We can write it as this term minus this term. So that's what I have here. You take that expression, plug that back into this integral, and what you would have is minus integral of this term, that's right here, and plus the integral of this term, where is that? Right here. So the integral of this term over the entire domain. Now that can be actually written down as, using the divergence theorem, we can split that, we can convert that integral over the domain to an integral over the boundary. So do you see that? This term, where is that? Yeah, this term came here. We are going to do the integral of this term over the entire domain. And when we take the divergence, when we apply the divergence theorem, we can convert this integral over the entire domain to whatever was inside the parenthesis dotted with the normal vector. This is the exact same thing that we just talked about in the heat conduction problem. This is divergence theorem and integration by parts for the elasticity problem. And it just involves a little bit of an algebra. So if you're not following that right now, then take a look at it again. And if you have any questions, just let me know. Or if you have any questions right now, let me know. So all we've done is rearranged our terms, and we are just doing integration by parts. So if you do integration by parts, you can write this weak form now with the derivatives that are balanced. So the virtual displacement has derivative ui has one derivative, and we are dotting it with sigma ij, which also has one derivative for the displacement. So this is a balanced derivatives on the displacement. And this is a very familiar form. This will give us the internal virtual work. This will give us the external virtual work. And we are also going to split the boundary into two parts the same way. One is the specified boundary. One is, specified displacement and specified traction. On the specified displacement boundary, we are going to say that our virtual displacement is 0, just like the same old one-dimensional case. And as a specified traction, that will lead us to the force term that we had before. Okay, so it's the same sort of setup here also. But there's a little bit of a difference from the heat conduction problem, because what we want to do now is to be able to write this in terms of symmetric tensors. So ui comma j is going to be represented with a matrix. Yes. This one? Yep, you're right. Thank you. So yeah, what we are going to do now is we are going to try to express this term into this form. ui comma j, this is the virtual displacement. We are going to try to find the virtual strain corresponding to this virtual displacement. So all we are doing here is we are going to take this quantity, write it as a sum of its symmetric part and the anti-symmetric or the skew symmetric part. So if you take this half and take this half, you add them, you will get back u bar ij, right? On the other hand, you have this uj comma I, which is just the transpose of that matrix. So ui comma j is a 3 cross 3 matrix. uj comma I is the transpose of that matrix. So all we are doing is we are expressing that matrix into the sum of its symmetric and anti-symmetric part. And if you look at this equation, the anti-symmetric part will cancel off, and you will get this. But the good thing about this is that we know that our stress tensor is also symmetric. So when we take the dot or take the double dot, so by the way, the double dot is actually an operator that what we do is we take element 1 comma 1, multiply it with 1 comma 1 here, and sum up all the terms like this. So for example, in the two-dimensional case, you have a 2 cross 2 matrix, and all you need to do is to sum up the corresponding terms. You would have 1 comma 1, 1 comma 1, and so on. So this is the double dot operator. This is a little bit different than scalar dot product or matrix acting upon another matrix. So the double dot product between two matrices gives you back a scalar. This is a scalar, right? So what I'm trying to tell you here is that you can express this product as this times the sigma ij, which is nothing but the virtual strain double dotted with the real stress. And this is nothing but the work done, the internal virtual work done in 2 dimensions or 3 dimensions. So this is also very similar to what we had in 1 dimension, and the contribution of this term will be 0 because a skew symmetric matrix multiplied with a symmetric matrix is 0. Double dotted with a symmetric matrix is 0. Okay. All right. So what we have now is all these different terms. We had this weak form, which says there is an internal virtual work term right here. There is an external virtual work term right here, and then right here. Okay. And now I've expressed those without indices also. So this is the virtual strain times the real stress, and this is virtual displacement dotted with the real body force. So if you dot them, that is nothing but ui bi. The same thing happens here. Given tractions, For some reason, the traction has gone, the bar has gone up. It should be down. So this is the virtual displacement dot with the real traction applied on the traction boundary. So this term and this term put together, they will give us the external virtual work. So this is again the same form. G is equal to Wi minus We. And now to proceed further, what we need to do actually is to start to use the void notation, where this is a abuse of the notation, but we are going to write this quantity right here in terms of strain and stress vectors. Those are not vectors, but we are going to rearrange our terms in such a way that we can express them as a dot product of two vectors. Okay, if we do that, what we are doing is we want to find this quantity in terms of the vector transpose times the sigma. So this is the virtual strain, and note that the off diagonal term of the strain, we have doubled that already because we need to calculate this quantity. So we have the virtual strain times the real stress. That is going to give us a scalar back. Okay, and if you use this void notation, you can express your weak form like this. So this weak form is coming straight from what we had here. This term, this was expressed with tensors. It becomes expressed now with strain and stress vectors. This term was the UB dotted. Now we have just rearranged that as U transpose up, that is a row matrix, a row vector multiplied with a column vector. That would give you a scalar. Similarly, this would give you a scalar. So what you have here is an expression for the weak form using the void notation. Okay, and so all that we need to do now is to discretize it. The same way that we discretized our heat conduction problem, we are going to take our domain. You can divide it into squares, rectangles, triangles, whatever. Okay, so we divide this domain into small parts, and we are going to write this weak form. We are going to write all these integrals over the entire domain as sum over integrals over the individual small elements. And if you do that, you will get this form. And let me, I think, so if you substitute this approximation in there, so this approximation is also a little bit different from what we had for the heat conduction problem or the one-dimensional problem. We are going to use this approximation, very similar to what we had before, n matrix times degrees of freedom at the nodes. So let's consider a triangular element. In this case, it's a two-dimensional problem, it's a vector problem, therefore each node will have 2 degrees of freedom. So in this case, I'm denoting the local node numbers as 1, 2, 3. Their degrees of freedom will be 1 and 2, 3 and 4, 5 and 6. So you can express the displacement at some point within the triangle. The displacement will be x times some displacement in the x direction, some displacement in the y direction. Okay, you can express those displacements with the shape function matrix, which is going to be written like this, times the degrees of freedom at all those nodes. So this is a very similar form, and if you take a look at the individual scalar equations, this is n1 times d1, n2 times d2, n3 times d3. The same type of thing that we had before for the scalar problem. So all we are doing is we are just expressing it in a little different form. So this is our shape function matrix. This is our degrees of freedom, and the same type of algebra that we used to find out the exact form. What is the form of this x y, n of x y? The same thing we are going to use for this elasticity problem also. So once we have the real displacements, we can also use the Galerkin approximation to come up with the virtual displacements, which is the exact same formula for n. Using the using the shape functions matrix now, we can also calculate our strains. Now these strains are again a vector. These are not a tensor. So the strain vector is going to be EXX, EYY, gamma XY. Those are that's the strain vector using the Voigt notation. And if you want to calculate that, this becomes your B matrix. So take a look at this. N1, comma 1, EXX is nothing but U1, comma 1, right? So U1, comma 1 is this times this times this times this. You will get EXX. EYY is the degree of freedom 2 times N2. So that would be U2, comma 2. So that gives you this row. Similarly, this is U1, comma 2 and U2, comma 1. That gives you this matrix. This is again all a bunch of algebra. You can make sure that all this algebra is accurate. But the idea is that once you have your approximation, n times d, you can get your strain vector, b times d, and you can get your stress vector, which is the d matrix. Now this d matrix was something that we talked about when we started to take a look at this. So this is the elasticity matrix long back that we talked about. Okay. So using all these approximations, you can plug them into your weak form and come up with the global equations exactly the same way. Yeah. Again, I'm missing a sign. Where is that? This one? Row 3, column 2. All right. Yeah. Thank you. N1, comma 2. Yeah. These are typos here. So this is N1, comma 2. This would be N1, comma 1. Are there any other typos? Okay. All right. So so the same idea you will use here, and you will come up with your global equations, and we'll talk about assembly and take an example next time. All right. So see you on Friday.